Okay, so to start with, the wood of the day, and people have been pointing out to me that I don't adequately show the wood of the day to those people who might not be here. This is, as you could have read on that label, black locust. Black locust, and this is another hardwood. You can tell it's pretty hard. It is hard. One of the harder hardwoods. Goes by a few other names. It says yellow locust, post locust, which I'm not surprised at because I know from my experience a lot of, particularly like farmers, will seek this out as to use for fence posts because of its strength and also good natural resistance to decay. So it seems to be the preferred fence post wood. We have up here in Michigan quite a few locust trees, but I think they're honey locust. I think it's a slightly different variety. I don't know how much difference there is really in the wood, but the black locust. As you can see there, it's kind of brownish, almost looks a little bit like walnut. It's not quite as dark as walnut, and when you cut it, sometimes it has a little bit of a green hue to it. It can have that white sapwood like walnut does. Those pieces don't, but apparently it can. Let's see, it's very heavy, very hard, and very resistant to shock, and very strong and very stiff, is what they actually say here. So I guess it is. I don't know that it's used particularly for tooling, for like tool handles. Usually hickory's the wood they use for that, but I guess maybe it could be. Maybe it's just more expensive. It's used for round-hewed split mine timbers. It's amazing how many things seem to be used for mine timbers. I wouldn't think there would be that many mine timbers, but I guess maybe it's the harder, more decay-resistant wood gets used for that. Also crating and stuff. It's usually not used commercially, probably because from what I've seen of the trees, they don't always grow that straight. They're a little bit crooked, and so it's probably harder to get, longer boardage out of it. Like dimension lumber would be harder. It is used. Oh, the other thing that it's used for, I thought was interesting. Traditionally, it was always the wood used for insulator pins. On telephone poles, they have those little glass pin, and they sit on a wooden peg, and those wooden pegs were always made from locust. In fact, locust was the traditional wood for all sorts of pegs in shipbuilding. When it used to be pegs, they were used for pegs in half timber construction, and the reason is because it doesn't swell it's very hard, decay resistant, and it doesn't swell very much. So you wouldn't want a peg that would swell because it might split the wood. So I guess that was part of the... Oh, hey, what happened to my picture here? Talking on, and I don't have my picture of... So there it is. Some of it's kind of creamier, some of it's darker. Let's see. This is like the locust we have here. I guess all of the locust has this kind of flower. Honey locust has a more yellowy flower, and it seems like they're a little bit smaller. But locust has these real fine leaves. I forget what you call that, where there's a stem and then lots of leaflets, all that come off of it. That it's almost like a fern, except it's a tree. So there's one. Yeah, you can see branches pretty early. That's from my experience, pretty typical locust. So it'd be difficult to get much timber out of that, but lots of shorter pieces you could certainly get a lot of pegs out of it, I guess. Anyway, so that's That is locust, black locust. Okay, so, and then otherwise today we're going to go on. Yeah, this is where we left off with the talking about the glulam. We got up to this design procedure, and we've not done. It doesn't seem like we've done too many. I mean, we're always analyzing them, but we haven't designed a lot of them. And there are a couple of techniques for larger, both larger timbers, and of course glulam is generally larger, that you can use to try to get an initial size. You know, in a design procedure, very often you make a guess at the size, then you analyze it, and you get to the end, and it either passes or fails. If it fails, you pick a bigger size. If it passes, you pick a smaller size. I mean, that's the iterative cycle that's often used in design. That's why tables are so very handy, because you can get a better initial pick, or you can pick it directly out of the table without the cycling through it so many times. Well, one trick, you've got to get dimensions, right? So one, to get the D in inches is usually a little less than the span in feet. So, you know, if you got 30-foot span, maybe a 20-something inch depth. And then once you have the depth, there's usually an aspect ratio that you can guess. Could be anywhere. A real stubby one might be 2 to 3, you know, down there. Well, I say 1 to 3. Okay, 1 to 3. Or, you know, usually they are deeper, and particularly with glulam, like this one in the photo there. Oh, wow, that's probably over 1 to 5, right? It looks pretty deep for the width. So if you get the depth, then you can use the ratio somewhere in here to get the width, and then you just analyze it, right? You get all your factors, you calculate the bending moment to get the actual stress, right? And then you compare that actual stress to the allowable stress and see whether it passes or fails. And that's where you'd have to revise it if it fails, or if it passes by too, I mean, if you think it's too inefficient, pick a smaller one. Then after you finally get, you go through until you get the moment to work, and then you usually go back through and check stress, bearing, because these things are usually pass, right? The stress normally doesn't control the design, but sometimes, I mean, if you have a very short, heavy, I remember you're talking about your exams that are coming up. I can remember when I was in civil engineering and they gave us an exam, and the whole semester long we'd been doing, you know, stress just passes, right? I mean, you check it. So on the exam, he gave us one where stress controlled. So you work through it, and you know, you get everything, and then stress fails. You go, oh my gosh, what do I do? So you pick the next biggest size and go through, and it failed again. And you go, oh no! The joys of exams, right? Okay, well, let's see if this goes through this lovely example here. Here we do have a 30-foot span, okay, and we've got the load given. We're going to use a point load, so this would be like a beam tying into it or something, plus its own self-weight. This is the, this is the point load. No, this is the point load. This is the live load, which is, does it tell us what kind of live load that is? Not quite sure. And the self-weight. Oh, here we go. Floor live load. Okay, floor live load, and the self-weight would be the W load. Okay, so we're given the wood. We pick that. This is the combination symbol. So it's visual grade 3, 20, that'd be 2,000 psi bending stress. Okay, see, right? BX. And we're, of course, assuming that it's deep, right? So we're using all the X values except for this one, which is going to be used for CL. We take the Y minimum for CL. If we did do the, I don't think I went through a deflection check, but if you did the deflection check, then you'd use the X, because that would be the bending in the X direction. But for lateral buckling, that's Y. Okay, and density in this case, I guess we have to calculate our self-load is 31.2. Oh, that must be based on the, if you look up the, they give the, what do you call that? Specific gravity. So then you can calculate the density based on specific gravity. So maybe that's where that's coming from. Okay, so here we go. Got to get these dimensions. So we've got a span of 30 feet. So if we take 0.9 times that, we get about 27. So we can take then maybe 27 for the depth here. And then if we're somewhere in this range, it looks like I took something closer to 1 to 5, one that's a little deeper. So that'll be 5. And here, you've got to, you can't just randomly pick a number. You've got to match the sizes that are available, right? There are these tables show you which widths are available. They're not all that many, but 5 and what I take, 5 1/4. There's 5 1/8, 5 1/2. Watch. Oh, 5 1/8 is what I took. Yeah, there's 5 1/8 is in there. Okay, so that's the 5 1/8. Okay, so we got that guy. The area then, this would be an actual member in the table. So from that point, you could just read the area and the moment of inertia, section modulus, all that stuff's in the table. Okay. This is table 1. No, I'm on the wrong pine. I'm on Southern Pine. Wouldn't you know it? Yeah, you gotta be careful. You're on the right wood here. Although I guess it doesn't matter for dimension as long as you find it. 5 1/8. Okay, by 27. They show it going all the way down to 36. Oh wow, that would be a pretty deep member, huh? So then we've got, this is table 1C. That's what I was going to say. Table 1C in the supplement. Okay. Okay, so we get those values. Then we can look up the strengths. This was Doug Fir, visual grade 3. There it was. We want the bending strength, right? This is bending in the x-axis, so that's that guy. And we'll want shear, right? We'll want the shear and hopefully shear x. Yeah, that should have been the number we got for the shear. Then y, EY min for the CL calculation. That should be that guy there. And this was what I was talking about. Maybe, I'm not going to guarantee it, but probably use, the specific, they give the specific gravity for the top and the bottom. Oh, I'm surprised. Where that? I'd never noticed that. Okay. So you have a density, in this case the same, but maybe in some cases not. Okay. Calculating the volume factor. Okay, so remember this is with bending, so in Glulam we got this volume factor. And here we've got the length is 30. We said the depth was 27, and this was 5 1/8, so 5.125. So this one comes out to be 1, right? And the others, I didn't write out the numbers, but apparently CV comes out to 0.89. Okay, so we got, and you're using this guy here, right? Other species. Gets put in there somewhere. Where does it go? Oh, for the, yeah, right. It gets put in on, right, in that power thing. Okay. All right, so now we've got that number. Now we're going to compare that to the CL. So we calculate CL. Here we've got a concentrated load at the center. And did I have, I forget whether it said it was braced at the center or not. Try and remember from my numbers here. Yeah, apparently, because LU's taken that. That's half a 30, right? So it is braced at the center. So we got with lateral support at the center. Should be this guy. And that, yep. Okay, that's what I'm using there. That's where that came from. Okay, so we calculate that. That goes down into there. Get RB. RB we use to calculate the Euler stress, and then this one, the only thing on it is the load duration factor. There's no moisture, and we don't put the CV on that calculation, I don't believe. Like we, yeah, and no bearing factor or anything like that. It's only would be temperature or moisture or some of those others, but we're not, the only one we're using is load duration. Okay, we got that. So that came out to be 0.739, which is less than CV, so we're not going to use CV. CV's out. And we just stick with the CL in this case. Okay, and the, I guess we got to calculate our dead load based on the density here, right? This was the density I'm using, the density, right? Density. And the area, and this is in inches, and this, I guess, is in feet, pounds per cubic foot. So we convert this to feet. This is a conversion to feet, right? Is what that is. So it comes out in pounds per linear foot. Okay, so that then is gets added here, right? This was the applied dead load, and this is the self weight over here. So those two, excuse me. That's not right. This is the point load. This is the point load. But I thought there was a, oh, I thought I had a dead load, didn't I? Maybe I screwed up here. Is that possible? Let me check real fast. Ah! 1375. Where'd that go? Plus self. Ah! Amazing. How many times I've probably worked this, but I don't see the 1375 there. This is the point load. Okay, so maybe I screwed up. I don't quite see. This should be the full W, obviously. So I don't know. I may have left one. I may have left out that distributed dead load. Okay. Anyway, you would get the moment. Hopefully, you'd get it correctly. This is from the point load, and this should be from the distributed load. Gives you the total moment. Then you use that to get the actual stress. Convert it. This is in feet, so this converts it into inches, and we get it in PSI. Then we compare that to our actual stress. Our allowable stress, and that simply has the one CL factor. The CD is also there, but that was equal to 1. Okay, so that comes out a little bit higher, so wow, it just barely passes. So now if I put that other load on it, I'd probably just fail. I have to go back and rework it and see. But anyway, in this, we'll say in this example anyway, it did pass. So then you'd be left maybe with checking a few things. You could check the shear, certainly. See, here I have it. What the heck? Where's that? Where'd that go? All right. Maybe looks like somebody forgot something there. Right. So that gives me the shear force. That's the end reaction, basically, right? 1825. And then the shear stress, 3/2 V over A for the rectangle. And that gives that. And then this was the straight value out of the table. CD would be on there, but that's 1. And I don't think there are any other factors that apply. So that easily passes. Okay, so there, even if I add the rest of the load, that one ought to pass. Okay, so you kind of see how that's supposed to go. That will wrap us up for, whoops, if I can get back over here, for the end show. Did it go away? Okay. For glulam, and now we can see we got an hour left, I guess. See how far we get with cross-laminated timbers. Interesting topic. Cross-laminated timber is really getting to be a popular topic. This is a pretty lousy specimen. I meant to look up these people. Structurlam. They sent me this sample a couple years ago, but it's like the world's worst sample. Holy smokes, look at the cracks in it. And it had obviously been cracked before they even sent it to me, because you can see where they repaired it. And they send that out as a sample? Unbelievable. Anyway, usually it would not be cracked, and it comes in much bigger, much heavier pieces than this, but you can take a look. At least the idea here, you can see the cross-lamination, right? The grain this way, like plywood. You can have a look at that guy. It's been used, I think it first was originally developed in Österreich, in Austria, and it went by the name of Kreuzlaminiertes Holz, KLH, and was used for. They had a lot of timber down in Austria. It's a beautiful country. If you ever get a chance to go there, wow, it's one of the prettiest places. Anyway, a lot of timber, and so they made use of it in this product, and then it was picked up in I think in Sweden they started producing it because they also had a lot of timber. And then it sort of spread throughout Europe. So it's used, I won't say it's it's certainly not the dominant material, at least not in Germany. In Germany, they use primarily masonry construction for like a residential scale, a scale of these things, or small, 3-story buildings or something. Two-story, well, whatever. And, but it has been used for some time. It's only in the past, 5 or 6 years started to appear in the U.S. There are, I think, now maybe 2 places where it's produced. They were going to start a plant here in Michigan, but it kind of fell through. They didn't do it. There's one down in Georgia, I believe, and there's another one somewhere else. I'm not quite sure where. It's produced up in Canada. That's probably where that piece came from, was Canada. And some of the Canada got a little bit of a head start on us. They were building some structures with it a little bit before we were, but now it's really starting to catch on in the U.S. And what's helping it a lot, they changed the IBC, the fire code in the IBC. There had been a provision that you couldn't really build with timber over, I don't know what it was, the limit was 3 stories or something like that, not very high, or there were pretty severe limits on it. Well, they did a lot of testing, and they more or less proved that it's actually, performs better in fire, like up to 3 hours, better than steel does. certainly better than unprotected steel, but even protected steel, because of the way it burns, it's so thick it doesn't burn rapidly. A light frame structure, of course, would go up like like a blaze, and this will burn as well, but it doesn't burn all the way through, so it remains structurally sound for whatever you want, up to 3 hours, or we'll take a look at that a little bit. So as a result, they've raised the height limit on the IBC, and now it is being built. There's a big one going up in Milwaukee. There had been one planned for Detroit, but then that also fell through. Okay, so you can see it lends itself well to prefabrication. That image at the top, this is Brock Commons. What the heck? I think my pen is getting defective. Okay, it went back to the arrow. Okay, because this is a new PowerPoint. Start over. Okay, this is Brock Commons. It's up in Vancouver, or where is it? Somewhere up there. And it's actually a dormitory on a university up there. And that, for a while, was the tallest building in the U.S., but I think it's been passed up now. You can see in this lower photo, too, they've even cut, like, openings into it, cut the slope on the roof there, it looks like. Doors, so it's prefabricated with to whatever degree you want. I mean, here, this one up in Brock Commons, they completely, all the exterior finish stuff and everything was added into it, but it's also being used structurally for this is a CLT too, that's spanning. So it's lightweight, it goes up pretty rapidly. That's the other big attraction of it. It's because it's all pre-sized, you bring it to the site and just lift it into place. It's very rapid construction. They say low environmental impact, I guess, and it does have good acoustic, even fire, believe it or not, seismic, because it's lightweight. So there are all sorts of great advantages. This is an interesting photograph. This is actually glulam, a beam, and this was an actual fire. It wasn't a test, and the glulam beam remained intact, and the steel, you can see, was not protected. Apparently, it was a smaller, not a very tall structure, probably only a couple stories. The steel failed. I mean, the fire got hot enough that's what happens to the steel in a hot fire, and it lost it. So here, this is a comparison of wood being timbers, right? A heavier, either glulam or this CLT, and over time. So in 20 minutes, this is the amount of strength that's lost. So steel loses 50% of its strength, and the wood still has over 80%. Steel loses 90% of its strength, and wood is still way up here at 75. So, yeah, it does a lot better. That's why we protect steel, right? I mean, although in this building it's not. It's all exposed. So if we had a fire here, that would be the problem. Our steel would quickly lose strength. It's not protected. Normally, I mean, they got away with that here because they consider this a two-story building. Kind of an interesting thing, but there is an entrance at the end of the hallway. There's an entrance from the ground level. So they say, oh, well, then this is the first floor, and below us is another first floor, or maybe a basement, I don't know. So, and then, so they kind of got away with it somehow. But normally, you'd have to protect your steel. Okay, here you can see this is the current IBC heights. Totally exposed, you can go up to 85 feet. So that's pretty high. and with no protection at all, just exposed. If you do it partially protected, I think that's where you put ceilings in. You don't have to protect the columns maybe or something like that. You can get up to 180, or fully protected, enclosed with gypsum board and whatnot. You could get up to 270. So you can get some pretty good heights from that. That's a. Oh, okay. Now I've got this is a good video showing the fire resistance. Let me see if I can. I don't want to click on it after all the problems we had. All right. Let's see. Is it coming over there? All right. Where'd my little mouse go? Come on, mouse. Where are you? There you are. Okay, let's see if we get this.
Wood buildings provide many economic and environmental benefits. Interest in constructing mid to high-rise buildings using cross-laminated timber, or CLT, is growing. New interest brings with it a natural question: is it safe? Forest Products Laboratory researchers and several partners conducted a series of tests that address concerns about the fire performance of mass timber buildings, and the results are promising.
We designed a series of 5 tests to investigate the fire performance of CLT.
To make the test as realistic as possible, we built a 2-story, full-scale structure at the Bureau of Alcohol, Tobacco, and Firearms Fire Research Laboratory.
The floor plan was a typical 1-bedroom apartment that we jam-packed with furniture to fuel the fire. Tests 1 through 3 were conducted without the use of a sprinkler system. Test 2 included 30% exposed CLT ceiling in the living room and bedroom, while the other CLT surfaces were covered with gypsum board. To begin the test, the fire was ignited in a lower kitchen cabinet. As the fire grew, a layer of hot gas began to form on the ceiling. The hot gas continued to expand until flashover occurred at about 12 minutes into the test, igniting everything in the kitchen and living room at once. From here, the layer of hot gas spread into the bedroom, and the process was repeated. The gas layer expanded until flashover was reached, and the entire room was engulfed in flames. Flashover in the bedroom occurred roughly 6 minutes after flashover in the kitchen and living room. Around 25 minutes into the test, the fire began to decay. After the fire started to die down, the apartment door failed at 30 minutes. However, the fire did not spread into the hallway, maintaining a safe environment for firefighters and people leaving the building. As the contents of the apartment burned out, the fire self-extinguished.
For the 4th and 5th tests, we explored the effect of an automatic fire sprinkler system on the fire performance. The CLT was left completely exposed for the 5th test, and we delayed the activation of the sprinkler system for 20 minutes. Temperatures soared to around 700 degrees Celsius, but once the sprinklers were activated, cooled to approximately 50 degrees Celsius in a matter of minutes. The sprinklers effectively suppressed the fully engulfed apartment.
These tests demonstrated that it is possible to build a cross-laminated timber building that's fire-resistant, even with exposed CLT. Researchers now have a better understanding of the performance of timber buildings under fire conditions. The data collected will help inform building codes, address the safety of occupants, and lead to safer firefighting in CLT buildings, allowing designers to bring wood buildings to new heights.
Okay, so yeah, impressive that it burned itself out, even with the, without the sprinklers. After, what they say, 20 minutes, or was it a little bit longer? It just dies down. So that's kind of interesting. I mean, what happened was all the, what would have been furniture or the wood they put in there that caused that, it initially burned, that burned well, but then when that was gone, it kind of died out. So the heavy timbers don't burn very well. Of course, those were protected, I think, in that version. And then the other was but even when they're not protected, what they say is it burns at a rate of 1 inch an hour. So it chars, it'll take a full hour for it to char through 1 inch. So what you do is you simply, if you want an hour fire rating and you want it exposed, you just make everything an inch bigger. And if you want 2 hours, it's 2 inches bigger, or 3 hours, 3 inches bigger, I guess. So, okay, that's quite a bit added, but, you know, that gives you the rating and it gives you the wood exposed, and it's not that heavy, so it's not too bad a price to pay, I guess. Okay, let's see if I can get back to my... No, not quite. Let me see, I gotta get my... That's the trick in this, is finding my mouse. Do you see the mouse on this other screen? Oh, where is it? Oh, there it is. There it is. Okay. Ah! Okay. Got you, mouse. Let's see if we can get back to the PowerPoint. I think. Okay. There we go. Okay, so it's typically, I think, always an odd number of layers, and it'll go then, you know, this is going this way, right? And then this way, and then this way, and then that way, and then that way, right? So this is the long span direction, and this is the shorter direction in the other direction. So you've got, just like plywood, it's just like plywood. You know, the grain on the top and bottom layers goes in the long direction, and that's the primary spanning. It does span in the other direction too, but it's weaker because the grain, right, it's which way the grain's going. You've got your grain going this way, that's going to be the main spanning direction on the top and bottom, and that's where the stress is greatest, right? So then it'll still, this layer will still carry it this way, but it's, look where it is, it's right in the middle, so that's not going to carry very much. On a 5 layer, you'd have it at least one up here a little bit higher. So anyway, and it is always an odd number of layers. They're saying 3 to 7, okay. It's usually, you know, sanded, kind of like the glulam is. They'll finish it. And okay, let's see what else we can say about it. It prefabricates real well, can be CNC routed. Now with all the CNC equipment available, this is another reason I think it's starting to catch on. You can make use of that. Typically they're up to about 10 feet wide, could be as wide. This depends completely on the manufacturing plant, of course, how wide they can make it. They usually can make it an infinite length, but the equipment is limited in width. But what really limits it is transport. I mean, you can only, you know, the trucks you always see on the road, they say 54 feet or 53 feet or something. 60 feet would be, this mentioned 60 feet. That would be very long. That would be, you'd have to have a label on your truck that said long load or something. I don't know how on earth they transport 98 feet. That would be tricky. Up to 20 inches thick. Okay, that's pretty thick. So those are kind of the limits of it. And now this is another video. And again, I think I'm going to click it. This was one that I came across that was produced, I think it's actually produced in England, but it's one of the best ones for giving an overview of not only the production, but everything about it. And this is done by a group, B1M, which has a lot of interesting videos on construction, by the way, if you are interested.
Cross-laminated timber, or CLT, is an engineered timber product that is threatening to upset the dominance of the big two structural materials, concrete and steel. Initially driven by the material's sustainable credentials, cross-laminated timber buildings are gaining traction, as they can be quicker, cheaper, cleaner and quieter to build than traditional structures. Over the past 5 years, the use of CLT in construction has risen dramatically. The material is now being used to construct impressive and sustainable homes, offices, schools and towers. Often referred to as super plywood, the material is constructed in a controlled factory environment from sustainably sourced timber. CLT is manufactured from spruce, although Scots pine, larch and Douglas fir can also be used. Once at the factory, the timber is planed and then kiln dried to reduce moisture content. The conditioned timber is then stacked into layers, known as lamellas, on top of one another. Each layer is placed at a 90-degree angle to the one beneath. These layers are then glued using a non-toxic adhesive and hydraulically pressed together to create the high-strength structural panels. Individual panels can in theory be any size. However, their width is limited by the size of the manufacturing machinery, which is usually around 11 feet or 3.5 meters wide. The length of the panel is only dictated by how it will be transported to site. While 45 feet or 13.5 meter lengths are typical for practical purposes, panels of up to 75 feet or 22 meters have been produced. Using state-of-the-art computer numerically controlled or CNC joinery machines, almost any shape of panel can be produced, meaning that door and window openings can be pre-cut in the factory. These off-site manufactured panels are then ready to be delivered to site. Fabrication is currently limited to only a handful of factories in mainly alpine countries, such as Stora Enso's in Austria. While this may require the panels to be transported to site by road, the embodied energy added to the project is far outweighed by the carbon savings. Proponents of CLT claim that producing timber building components consumes only 50% of the energy required to produce concrete, and a mere 1% of that needed to produce steel. The prefabricated panels can be delivered to site as they are needed, making this construction method ideal for schemes with limited on-site storage capacity. They are then lifted into place using pre-installed lifting straps and rapidly assembled, greatly reducing construction time and therefore cost. As the timber used is kiln dried, CLT should not shrink or warp when on site. However, like most timber elements, CLT must be placed above the damp-proof level and will need protection when used on the external facade. CLT construction can also reduce the self-weight of a structure compared to concrete, potentially reducing groundwork costs. The construction process is also cleaner than traditional methods, with greatly reduced levels of dust. It is also quieter, a distinct advantage for projects built in urban areas. While there are numerous benefits to CLT, some people are fearful of living or working in timber buildings. Some believe these structures have an inherent fire risk, particularly when rising to 10, 20 or 30 stories tall. Unlike unprotected steel, CLT can remain structurally stable when subjected to high temperatures. When exposed to fire, the outer layer timber chars and forms a layer around the structural core, which can retain its load bearing capacity. CLT's inherent fire resistance allows it to comply with fire resistance classes, withstanding blazes for between 30 and 120 minutes, depending on its engineering and formation. CLT uptake and use was initially driven by the material's sustainable credentials. However, in recent times, a resurgent construction market that is placing pressure on traditional materials, along with increased awareness, has bolstered adoption. While early CLT buildings were predominantly small, low-rise structures, the material is increasingly being considered for taller schemes. Since architect Ward Thistleton built the first timber skyscraper, or plyscraper, in 2009, tall timber buildings have been planned around the world. In the past 5 years, towers of 30 metres, constructed from CLT, have risen in Australia, America and Europe. If you enjoyed this video and would like to get more from the definitive video channel for construction, subscribe to V1M.
Okay, subscribe to V1M. All right, so you can see they quite a few taller buildings now. Let's see if I can get my back to my I think I'm there. Okay, the from the APA, this is their main piece of literature. This is the PRG 320, which should be up there, in the files on Canvas. This has some background information about the manufacturer, the size, the tolerance, all the stuff we've been talking about, but it also has, somewhere in here, all these strength tables. So it has basic, just like our supplement, basic strength of the material, and then they give strength of the assembled what do you call them, panels, right? So this is just the material strength by grade, and these tables are already for thicknesses. So you'd say, oh, I've got a 6 7/8 E2 grade, and then I can come across here and see exactly what the strength of the panel is, not just the material. So they give it to you both. You can calculate it. You can use this to calculate that. A little bit of trouble maybe. What else do they give you? Other information. All the equations that you would need to do the calculations happen to be in there too. Woodworks, which is that's separate from APA. Who's Woodworks? Wood Products Council. They've got what they call the Timber Manual, which is also pretty detailed. I don't think it has any stress tables in it, but it has a lot of connection details in that, which is useful. And let's see, the biggest one we'll talk about in a minute. This came out in the U.S., which worldwide is probably the best resource. This is the TLC handbook, and this was a group effort from APA and the Wood Council and the Forest Products, and this whole group of people down here, and they did a terrific job. I have a friend of mine that's an architect in Sweden, and I took this to him and showed it to him, and he was just amazed. He said, wow, we don't have anything to compare with this in Europe. I mean, as far as a comprehensive manual, because it's not, it gives all of the details of construction, details of manufacturing, but then it also goes into all the fire ratings. It goes into acoustic properties. It goes into thermal, calculations. So it's very, very good manual. And there's a copy of that. I put a PDF of this up on the Canvas thing too. Now, here in North America, actually up in, it's Vancouver, British Columbia, at the University of British Columbia. Yeah, it says that there. This was the first really tall structure that was built in the U.S. Not that tall, 18 stories, but still pretty tall. It's now been surpassed by, I think the one they're doing up in Milwaukee is 28 or 20 something, I forget, up there. Anyway, you can see it has a concrete core, right, that gives it the lateral stability. 2 concrete cores, that one's also, and but then it's all these plates and columns, and the bottom layer lifted off the ground was concrete, and I think is used as a parking garage or something. This was is a dormitory, And I've got also, I think we got time to, there's a lot of information about this online because it was the first real, I mean, it was really promoted. Let's see, this is a longer video, but I'm just going to show you the beginning of it, and then maybe I'll post it and you can... This video goes on, and it goes on for like 10 minutes. They interview the architects, they interview the engineers. It's a very interesting video. So I'll post that, and you might want to take a look at that. But that was quite a project, and you can see this one was also in a urban kind of setting. I guess it was on a campus, and there was not a lot of room to set material. So they'd pull a truck up and they'd immediately offload that truck, and the truck would drive off. So there's that's a big advantage of it, that it's immediate. You don't have to store it on site. The truck drives off, you go directly from the truck, prefabricated pieces drop into place. It was a pretty interesting project. The columns are all Glulam. They have little metal connectors at the base, and they just take the columns and plug them in. It's almost like what was that we used to play with, Tinker Toys or something, that, you know, where you just plug it into the pieces, go together. So it does have that advantage, the rapid construction, lightweight, and in my mind, I mean, it's kind of a nice. The wood is certainly more beautiful than concrete anyway. Okay, let's see. I got a little trouble getting back to my... Okay, so this is the CLT handbook I was talking about. Let's see if I can... These are just some of the tables out of it. This is the strength table. Gives it for the major axis, of course, major axis and minor axis for all the stresses by the grades. These are machine evaluated grades and visual grades. The same as for Glulam, basically. These are the adjustment factors, very similar to what we have in the NDS. In fact, the CD is exactly the same. Wet service factor. You have to look up the... Actually, they're probably in here, but this handbook has them as well. And then these are the other tables that I mentioned. They're in these are, I'm taking them out of the CLT handbook, but they're exactly the same table in that, this one, the PRG 320. These are the design tables where it's by, by panel. So you have a particular panel, and then you can read across and see what the, and this is the layup, right? These are the layers. So this one would be 1, 2, 3, 4, 5 layers thick. Okay. Okay. CD, CM, CT, same as what we have in the NDS. This is where it starts to get a little bit hairy. Calculating the bending stress, right? So we're going to get the stress is M over S, right? So we've got to get S. There's S, and to get S, you need would normally be I over C, right? You need the I, and to get the I, the problem is it's you've got different E's for whether it's going that way or that way. So it's not a homogeneous material. So you've got to calculate, if you want to calculate that I, you've got to do it by the parallel axis theorem. This is, summation of I's plus summation of AD squared is what I usually write it as. And that's by layer. So these are rectangular, BH cubed over 12, that's the I, but then it's got the E has to be factored into it because that's what's changing. The material stiffness changes, so you got to consider that. Okay, and then to get this, EI apparent also gets, that we're using, I think, the effective on that other calculation, right? This is effective here, but the apparent gets used for, I think it's shear and bending, and shear and deflection. This is the factor for shear, the modulus of rigidity, right? The shear stiffness has to be calculated in here. This is the modulus of rigidity down there. And so it gets also a little bit complicated. Fortunately, all these values are what they put in the table, so you don't have to do these big calculations. They're just, but that gives you can see where they're coming from, which is nice. This is all the KS values that go up in there for the different fixities conditions. Okay, so then this is the shear calculation where you've got, right, normally you'd have VQ over IB, right, would equal the stress. So this portion, what they've done is they've separated it. They want to calculate it for the strength, so they're saying, whoops, the V is equal to the stress, and then this has got to flip, right? IB over Q. So that's why they figure that component is what's going down here, so that you can calculate that. So it's just the normal formula, but it looks a little hairy because you've got to calculate, the different layers. So that's figuring that. These are much simpler than, this is just P over A, right? Your strength, but notice they're only using the parallel layers. They just totally neglect. So if I've got it like that as a wall, that would be my wall. This would be a big mistake to make the wall like that because I'd only be using that layer, right? You neglect the layers that are being squished. You know what I mean? The neglect the layer with the grain going the wrong way. So this would be the way you normally use it, and you just use the layers that, but normally it's got enough strength like that, so that's not a big issue. Here's calculating CP. Again, you've got to use this. This is where the AP min goes, the apparent minimum EI. for the Euler stress. It does get this same C factor that Blue Lamb uses, and otherwise it's pretty familiar. They've written it all in terms of force, though. It's in terms of force rather than in terms of stress. Okay, and that's because you don't want to deal with the, I mean, you want to look at the force on the whole panel rather than this, try and that's because the stresses are different for the different layers. Okay, and here we again, only looking at the parallel layers in tension. Okay, got that. And this is, oh yeah, we haven't gotten into this yet, but I think we will in a week or two. Combined bending and axial load and bending and axial load, right? Combination stress. So that's a little bit, it's simply adding them together. This is the axial over here, and this is the bending over here. Okay. And last but not least, bearing. And bearing's pretty simple, right? That's another P over A. And this calculation of FC asterisk. All right. Okay, so I think we've still got time to do a little example. This is actually an example that's in the PRG 320, I think. I got this out of here. I saw it somewhere. Anyway, so we've got a long panel, 30 foot long. This is the length, right? And it's this E1 grade and 5 layers thick with a thickness of 6 7/8, right? So we've got 1 3/8 layers times 5, right? 1 3/8 times 5 hopefully is 6 7/8, and the top, and we're going to do the flexure in the strong direction, right? This is the direction we're going in, right? Okay, so we just want to get the load capacity. So I think I'm given, I take probably the self weight as a dead load, and then see what the live load capacity, or the total load capacity. We'll see. I forget how I did this, how the example goes. Okay, so first, E1, the grade, and this is out of the properties tables, right? So I'm going to do I'll go through the long calculation first, or at least show you the equations, and then you'll see how easy it is actually to use the other tables to pull the values out. So here we get the bending stress, the allowable stress, and the E modulus, and we'll use that in the strong direction. Actually, the weak direction also comes into it. That'll be the weak direction, and the stress for the E modulus rather for the weak direction. Okay, so here's the big summation of I plus summation of AD squared, right? That's that equation, and it's just broken up by layer. So the outer layers, layer 1 and layer 5, and the layer in the middle, those are the ones that have the wood going in the parallel grain parallel to the span. So they have the strong axis E modulus, so that goes in there. The other ones are going the other way, and they use the 1.2. On top of using the 1.2, they divide it by 30 as a reduction factor, and I didn't see a big explanation about it except that they do it. So I guess that's an additional reduction on the weak axis bending. Okay, and then you plug that all in for every layer. You've got to get the Z's, right, the heights for the AZ squared here. And you sum that all up and you come out with 440. So you can see it's a bit of calculation if you really want to do that. But like I say, in a minute you'll see it's in the, you don't really have to go through this. But this would be the equations that produce the tables. And this is the major axis and this is the minor axis. These are the values we saw in the table a minute ago. Okay, so we got all that. That number then, we're calculating the section modulus, and this is what we just calculated, the EI effective, and that equation for the section modulus is this, which then gives us that for the section modulus. Okay, that goes down there. This was out of the table, right, that we looked up. This is an additional safety factor that they stick on it, okay, for flexure, and conversion to inches, and it comes out to that in foot-pounds. So then that would be, that's the moment in foot-pounds, right, that's this guy, and then that that's what, oh, this is, sorry, I shouldn't have said that. This is the actual, right, from the load, WL squared over 8. All right, then we do equate them. I guess I could have said that. We do equate to find the load. We set the actual stress equal to the allowable stress, right? So this will be in terms of moment. We set the allowable moment, or the strength moment, equal to the load moment, and then the unknown is W, so we calculate the W. So I guess I did that combined dead load and live load together. So you get a total of 92 PSF, and then you'd have to subtract off your self weight or whatever dead load was on it to see what's left for live load. But it looks like pretty much. So that shows you how that works. And then to do it with the tables is a lot simpler. This was our thickness, wasn't it? Here's the E1. So you just look up the grade and the thickness, and then you read across. There's the force, right? The bending moment, essentially. F times the section modulus. So there, immediately I can pull out the strength of it. So it's pretty easy. And then this is, they give you the other numbers as well. This is the what we were using for the EI effective. So you can have that. And then they give it to you in both axes. You can have it for the minor axis as well. So that makes it pretty easy to design with. I mean, you can immediately pull out the strength of it. And those are the tables that are in the PRG 320, or they're also in the handbook. Okay, now I thought we could look a little bit at some of the construction details, connections. A good source for this, there's a lot of them in the handbook. There were, where else did we see them? In this timber construction manual, I think they had a bunch of them, didn't they? Yeah, in the timber construction manual, they also have a lot of these. These that I pulled out, this is from some information that was online from KLH. That's the Austrian firm, Kreutz Lagenden. I think it's Kreutz Lagenden Holz is what that stands for. And they're all pretty much the same. People are doing it with these little steel clips. Here's lifting it up. This is a concrete base, so they're lifting it up off the concrete, maybe with a waterproof. This has a little waterproofing layer here. This is a little bit more waterproofing there. So you've got to make sure you separate. If you've got concrete, you never want the wood to sit on the concrete. I think that's a bad idea. I think I told you the story of the church in Detroit I looked at. The floor was collapsing because they had done that. It eventually, it's not good. Anyway, then they make these little wooden clips that just attach it and clip it down. Here are some others where the clips are connected. They'll also use screws to join them diagonally like this. And these are long. I mean, these screws can be a foot long because they're depending how thick the panel is. So when they install them, they're usually pre-drilled, and then you've got a jig that, I mean, it's not like you just turn the screw. It's you guys set it up to be able to do that. I think I got it. Oh yeah, here's a picture of it. So they'll set them up with a jig to make sure you maintain the angle. So that's a lot of screws, but it makes, I mean, that's typical of wood, right? You try to spread the connector out so you don't have a constant, you don't want it like steel where you just put a bolt in because the bolt would concentrate the load on the wood and just crush it. So you got to spread it out with lots of little fasteners. Okay, so that's more of the screws. What else we got? Yeah, these are floor panels then, different ways to attach those. And then this was a little project in Münsterlinde. I think that's in Rhineland somewhere. Lüdinghausen, wherever that is. Looks like a pretty gray sky. Must have been in winter. But I think they do the whole thing in 2 weeks. So this is kind of a segmented, starting with the foundation, and then they deliver these on site. The Germans will be very accurate at placement of things, and you can see here they've got a little laser, what do they call those, spotting device, so you can precisely place the pieces. And then they just put them down with these little clips. I think you can see the clips here. See, the clips are already fastened in the foundation. They went around and put those in first, and then came back and put the panels in. And here within, I don't know what the time on this was, looks like a couple of days, they already had the whole first floor in. This is the end of week 1 here. So they've got the panels placed. They're all delivered to the site, prefabricated with the doors cut in them. Put the roof, put the second floor on it, and then this is the attic floor, which is cut for the roof. So they got that all done in a week. The second week, they're already putting the roofing on it. This is a heavier, this typical European heavier roof, and then they put tiles on it, probably. We'll see. This is where the kids sleep upstairs in the attic space. And this is the tile roof going on the exterior at the end of week 2. So 2 weeks, they get it totally enclosed, roof on it. I mean, they still have to do the exterior, I guess, and finish the inside, but that's pretty rapid. So let's see. Residential kind of stuff. This is an example that just shows some a lot of CNC routing. This is one they put together. Forget where this was, but it was all prefabricated and cut. It's a double layer system, so they have 2 panels that are all fitted together, and then they transport this as a unit to the site and then drop it into place. So this was the CNC setup. There's their cutting equipment. You can see they've got a space a little bit cleaner than ours downstairs, but and pretty big to assemble it all, and overhead cranes to lift it, and then they transport it to the site, fits nicely on that truck, and drop it into place. So they had a whole series of these panels that fit together and produce this, us in Switzerland, Lucerne. There we go. Yeah, so that was a project. These are some other just examples of European work. Augsburg, but it does show you the potential of the interior space all in wood like that is really kind of nice. These are some in Australia. I think she even showed one of these in that earlier video. These are some of the earlier structures that were built, 10 stories. They built several in Italy, in Rome. This is one in the UK that was put up. And you can see, again, with these little clip fasteners, piecing it together. This was that, right? The honeycomb had a nice open interior. That's the outside of it. And this was one here in the U.S., a more recent one, which just finished in 2019. This is part of the university, I think, Georgia Tech in Atlanta. And I probably have just time to show you. This is a completed structure. Beautiful interior. And they did a little time lapse of this as they were building it, and maybe we can close with that if I can get my Kindle. Let's see if we get that guy. So this is pretty rapid, but this is the site prep. All concrete foundation, and then they come up off of that with the CLT elevator core. So it looks like much more of the work, the majority of the time looked like it went into the foundation, because look at that bang. It's what, 2 days, and they put the whole frame up. It goes much faster. Yeah, it's Atlanta in the background. Nice columns, steel brace columns. So that was their that project. Not very tall, but it is kind of a interesting use of the CLT. And it to me, the interesting thing is you see in something like that how long it takes to get the site prepped, the concrete. And then when they put the CLT up, it was like literally, 2-3 days, and they had that all framed in. So it goes pretty rapidly. Okay, very good. We did get through that. But I don't know. There's a discussion about maybe not doing the STAD next week. But what's going on here in the school as far as exams or anything next week? Are they again final? Or when's the due date on projects? Is it before or after?
Mine is after the break.
After the break, huh? Well, we'll see. Maybe I'll do this. Maybe I'll go ahead and explain the STAD, and then we'll just have a work session on Thursday, so you don't necessarily have to be there for that, because I'll do the whole explanation on Tuesday of it, and then you can play with it over break if you want. We'll see. And then we can talk about it maybe more when we come back. Yeah, all right. We may do that. Very good. Watch out for the snow. We're supposed to get, how many inches this afternoon? 7 or 8? You don't think so, huh?
I don't know.
I don't know. By 3 o'clock, we're supposed to be snowed in.